Okay, so today's video I'm going to try to explain why the fourth dimension looks, as many people have put it, like shrinking and then expanding, right? This is what people say stuff is in the fourth dimension, right? So let me start with a very simple premise, right? I have this. What is this? It's conventionally defined as an axis, right? The x axis. That is x and minus x. These are the axes. My problem is that I want to connect the x and minus x axis. Well, how do I do that, right? Well, simple, just connect them, right? That's a really good solution that will possibly give you some closed shape. You don't need to necessarily make this a circle. You could make this a circle, you could make this a square, you could make this a triangle. Any closed shape could now be the x-axis since it is essentially connecting with itself. But let us take circle for the easiest interpretation, right? When you select something, you usually circle it. So this is the point. This is the shape that we are going to connect stuff with. And let this be known that this works for any closed figure. So essentially what is happening is that we have discovered a closed surface, right? Where one positive side of the axis is connected to the negative side. But what if the problem was a little complicated, right? Well, what if instead of one axis, since we live in more than one dimensions, what if I have two dimensions now, right? Y minus y, x and minus x. How do you connect these dimensions? Well, simple, you use what we have applied, right? So you connect x with x and you connect y with y. Voila, you've got a sphere, right? This is a good shape that connects the y-axis and the x-axis, and in two dimensions, this is the base of a sphere. What if we go one step further? We want to connect all three axes, like the three dimensions that we have, we want to connect all three. Mind you, this circle and this circle are of the same size. So let's start drawing. We have this circle of the same size, we have this circle of the same size, and we have this circle of the same size. That does not make sense. Or does it? Well, instinctively, right now, you cannot have three circles occupying the same space, but you can. In a four-dimensional shape, it would be a same sized circle that would be occupying the z-axis. And this is what a four-dimensional sphere would look like. Take a square though, take a square here, you get a cube, and then you take a square on this side and you essentially get what is a tesseract. You have these connections which are basically that of a cube, right? When you have this, you can draw a cube out of it, but you also have this, which all of them are of the same size. But yeah, this is tough to comprehend. But let us try to comprehend it, right? Well, okay. What if I had another question, right? We try to solve this. What if I have the x-axis already in a circle? What if x-axis is connected? What if I want to connect the y-axis to itself, but along this x-axis? Now this is the x-axis. So essentially, as I go along the x-axis, at one point I am going to connect with myself, right? So this just needs connections. I just connected it, right? I connected it to itself. So this is a simple thing that just happens, right? Okay, now notice, as minus y is this side, y is this side, minus y is this side, y is this side, minus y is this side, y is this side, and now minus y is on the other side. So essentially, what we are doing by going around the x-axis, but halfway, is we are essentially just rotating the axis by 180 degrees. Right? That is a very interesting way of looking at it. What I just did is I just flipped the axis, right? This. And then this again continues. There'll be minus y here, minus y here, until it unflips again. That is why 360 degrees is rotating by 360 does not make a lot of sense, because that is the same as rotating by 0, which is nothing, right? And this is interesting. But this is too simple. What if I asked the question that I wanted to connect the y-axis minus y-axis? Now this is the x-axis, right? We defined it. But what if I wanted to connect the axis, but in a certain way that minus y becomes the y-axis as we move along? Well, this is different because I'm not just connecting minus y to y to minus y. I am doing that, but I am also doing it as we go along this closed figure of the x-axis. So how would I do that? Well, simple. Let's just try to go along it and see if I can connect it. There we go. Connected. Minus y, this axis, is now connected to the y-axis. And as the y-axis progresses, it's connected to the minus y-axis. Well, voila, we did it. We did this. Let's try to understand what we did though. Right. We have this. Till here, everything remains the same. We have minus y and y. What's happening here? What's essentially happening is, if this is the x-axis and this is the y-axis, what I am doing let me try to do it step by step in a certain sense. That will be more clear. See, this side is going to go this side, right? Here, 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 here. And then this side is going to be touching this side. This side is going to be touching this side. Here, 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 and here. And what I've essentially done is introduce this concept of a twist, right, in a certain sense. This is the minus y-axis, this is the minus y-axis until this twist point. And it'll be better if I make a different shape, perhaps. Right, this is the shape, which is not that bad. Like, if you look at it as a very thin slice, this is just a very prominent shape in mathematics. Actually, it's called the Mobius strip. But this is nothing special. What we have done here is, I have the minus y-axis. Let's just track the minus y-axis for now, right? Minus y goes here, goes here, goes here, goes here, goes here, 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 here. And just as we reach this point, you notice this circle, as we are coming here, it's continuing on this side, if you noticed. So this is the minus y-axis, this is the minus y-axis, and whoa, we reach here and this is the minus y-axis. And then we go on, the minus y, minus y, minus y, minus y, minus y, minus y. This is the minus y now, and then this is the minus y, this is the minus y, this is the minus y. We reach minus y over here, and you see this is now minus y because this circle is connected to over here, right? Minus y, minus y, minus y, and oh my god, I just connected a line to itself, essentially. Wow, this is just two lines that are connected. So there is no concept of a minus y side or a plus y side to the axis anymore. Now this is very interesting, right? Because we would not expect this to happen, but this is a very interesting behavior. Now you notice what happens here, but just keep that in mind. Now what I want to do is essentially extend this, right? I want to extend this to 2 dimensions. So instead of taking the x-axis, which is enclosed, because I want to use the xy axis since that is how we understand 2 dimensions, let us assume the z-axis is enclosed now. This is just so I can actually plot x and y. X and y are supposed to be perpendicular to the z-axis mutually. And so we have this, perpendicular, 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 right? So this is the y, this is the x, minus x and minus y. Now I ask the same question. What if I want to connect these axes, but as I move along this route, right? As I move along this route, what's going to happen is essentially as we move along, nothing happens to the y-axis if you notice. It's constantly a straight line, right? So nothing changes for the y-axis, but like what happens to the x-axis here, the x-axis flips sides. So essentially a minus x here and x here. Okay. So now what I want to do is again do this, right? I want to connect x minus x to x and x to minus x. So take note, this is minus y, this side is minus x, this side is minus x, okay? Minus x. So what I do is I take the x side, connect it to minus x. I take the minus x side, connect it to x. What have we done here though? I don't know. This seems very weird, right? And essentially it is in a certain sense. It's very weird. Because what happens is that you have essentially created a Mobius strip over here. This is simple. And this is the fundamental aspect of a Mobius strip, right? But what I'm trying to do is I'm trying to track y, right? What's happening to y as we do this? As x is constantly being shifted, right? My bad. This is what's happening to the x-axis. It's shifting. And we try to draw perpendicular y's, right? This is the x minus x, x minus x, right? You notice as we reach this point of where this is changing, the y-axis essentially also flips. Because when you look at it in 2 dimensions, something that is perpendicular, right? Okay, let's try to notice what's happening. Here it stays y and minus y. This is still x and minus x. But as x is shifting, right? It's shifting this way. The y-axis also undergoes a shift. Where if you did not notice, okay, let us just follow this y-axis, okay, all throughout. The y-axis, since this x is over here, right? X is over here, that x is over here, and that x is over here, right? So as you see, I'm drawing the positive y-axis over here. It's over here, it's over here, it's over here, and over this side it's opposite. It's on the opposite side. It's y is over here, minus y is over here. And essentially, we have just inverted the axis. So what we get here is we are connecting essentially also minus y to y and y to minus y. But we don't want that. We just want to connect x to minus x. Okay, let's try to think of this in a useful way. We have x, we have minus x, we have y, we have minus y. We have minus x, we have x, we have y, and we have minus y, right? So x connects to minus x connects to x. Now what I want to do is I want to make sure that y connects to y. So as I move along this circle, I am also ensuring that y connects to y and minus y connects to minus y. So what's happening? Well, essentially, when we go through the script, you see how this is getting complicated to comprehend, right? Everything that's happening is happening in this little region, and I'm trying to analyze that. So when you have y, right, here positive y here, positive y here, positive y here, but you notice as it shifts, I'm making sure that y remains constant, right? There's a dimensional way of understanding this, in a sense that this is a shift, is a turn that's happening in the second dimension, and in the third dimension, because one dimension of x is used up. So let me just take you here, right? Here we have this. Okay, this is the first dimension, which is basically the z-axis, right? We use that to connect with itself. When we were attaching 2 to 1 and 1 to 2, what we were doing is essentially a shift. But the shift was not in the second dimension that the x-axis is supposed to represent. But no, the shift was in along the y-axis, right? The shift was like this, like this. That was along the y-axis. That was along the third dimension. And what we are doing is essentially now we want to make sure that this is remaining the same. So we are undergoing another shift that is in the fourth dimension. Now this is a much simpler way of understanding it. So what I've done here is that this is the x-axis, which is going, it comes over here. You have 90 degrees. This is the Mobius strip. But we are making sure that y connects to y and minus y connects to minus y. But since we only have access to 3 dimensions, right? You only have access to 2 dimensions currently. Because it's a board, what you would see along the third dimension is as this passes on the y-axis, essentially also has another form of a Mobius strip. But this Mobius strip, this turning, is happening in the fourth dimension. And what we can see essentially is this is an elongated version of a Mobius strip. This will make it clearer, actually. You get it? Sorry, this is disconnecting it. So essentially, if I draw it better, if I connect it better, let me just restart. This is a turn, right? This is a simple turn. There's no twist over here. But when I want to connect this with, this is minus x, and I want to connect it with x, and x, or minus x with x, I'll have to do this. Which is essentially, since this is going along the first dimension itself, this is, and we are taking the second dimension along with us. This is a turn in the third dimension in a certain sense. You're not even twisting, you're just turning in the third dimension. But what we are also doing is making sure that while we turn, essentially this remains the same. So when you take a look, right, if these are 2 points, these 2 points, as you look at it from the other dimension, they appear to get closer. Right, and since this turn is happening in the fourth dimension, the third dimensional beings, the third dimension is itself going to appear to shrink in a certain sense. When all we are going to do is just turning across or moving across the fourth dimension. And that is why size perception matters, because from a three-dimensional point of view, when you look at this 2D object, I can tell you, and you can maybe understand that even though the sizes are smaller, it is just turning, it's coming closer and farther from me and towards me. And since it's coming towards me and it has to maintain the same structure while turning, technically the size is decreasing because it has to be in a continuous loop. And so anything that's towards me and the same size should continue to technically, okay, let's not get into the jargon there, but as you see, this from a particular vantage point appears to shrink even though they have the essentially the same size. And so what happens when four-dimensional structures are involved, again coming back here, is as this sphere tries to connect with itself, this two-dimensional object that has two dimensions, as it tries to pass through a similar circle, what you would see is it shrinks in a certain sense. And then it enlarges. And what it is essentially doing is just traveling through a connected space of the fourth dimension. And I don't know why I'm drawing this circle as large. It is essentially the same space as this sphere. It is not occupying more space. And essentially, that is why we see this sphere itself shrink and then enlarge. And I guess that is one way to look at why four-dimensional objects behave in this shrinking, enlarging way, which is fun.